I think we can start. So there was a typo on the lecture something when I defined the energy of the Hopfield network. So, so, um, so the energy of an Hopfield network is this. Without the half. This happens because, I mean, on the slides there was this written with the half, but equals something without the half. And on the blackboard I wrote it without the half. Let's try to understand why there is no half, because I think this is interesting. This is the definition of the energy that we gave for the BAM network. Minus a half x w y transpose plus a half v w transpose minus a half x theta transpose. So there were two parts with the thresholds. That's because we have different thresholds on the left layer and on the right layer. But I told you that the link between Hopfield and BAM is the fact that we're making coincide the two layers. So it's kind of like, in this case, there will be theta and theta again. So you sum them, and that's why you don't have a half. So it's not taking just half, it's not cutting a BAM, it's actually overlapping that. So this part is the same, because this is equal to x again, and this is equal to theta, and this is equal to x. And so that's why we come with the term that has not a half in front. So that's it. What else? So I wanted to make a last example about Hopfield networks to show how those things are used to solve a problem, in particular how to use the energy of the Hopfield network to solve a problem. And then we were gonna go to yes. So then we're gonna go talking about preliminaries for independent component analysis. Independent component analysis is the topic of the second half of this week, and Vadim will take care of that because we're splitting the course in half, so it's his turn. So yeah. What else? So basically today I'm not going to talk about independent component analysis, but I'm going to introduce all the math you need for independent component analysis. Yes, so let's talk about this. So I made you an example of a Hopfield network at some point that was called the flip-flop. Yeah. And I made it as an Hopfield network with values -1 and 1 at power of 2 actually. So let's make it with 0 and 1, and I will show you after why. But basically, the objective here is to generalize this concept of flip-flop. The flip-flop as a stable states 1 and -1 and -1, 1. And so if you try to write it instead of -1 and 1 with 0 and 1 at the power of 2, what you obtain is this. The dynamics has the following form. Sorry. Also, there is an announcement. Some people asked on the anonymous chat about the exam being able to do it online. No, we do it in presence. This is a physical university, so the exam is here, either the 16th of December, and we're going to open a poll to decide the second date that will be in the month of January after the 8th of January. So you can decide the second date, but the exam, you have to be here to take it. So this was the dynamics of this flip-flop, but I just put zeros and ones instead of a one. 1 and minus 1 is the same thing. You remember that it had as stable states those. I don't know if I have to write the network. Maybe yes, maybe no. Is this really useful? Let's do that. So this is the flip-flop on 0 and 1. You can put as threshold theta 1 equals to minus 1, and theta 2 equals to minus 1 as well. Minus 2 as a weight. Whereas the activation function is the Heaviside step function of threshold theta I. The same thing before we had minus ones and ones. Here was 1 and threshold was 0, but if you glue this to what I had told you about the flip-flop with minus ones and 1, is the same, and it is the same dynamics. Those two are stable states, clearly, so it's kind of, we say that the network stores the stable states. So, and wherever you are, you will converge to this, to one of these two, and stay there. So, what is the generalization of this concept? It is called multi-flop, and tells you basically I want a network such that it has n units, fixed values in 0, 1 at the power of n, and I want to find the weights and the thresholds such that the stable states of my network are of the form all zeros and a single one. So this was like all zeros, just one, and like this is the case of n equals to 2 if you want. So if you have n equal to 2, you have this, okay? And now we want the same thing, but for n coordinates. So the solution to this problem there, like the picture is for n equal to 4, and you find that all the weights should be equal to minus 2, and all the thresholds should be equal to minus 1 for all r. Why does this network converge to a, as stable states, only the vectors with a single one? So, for example, for the case of n equals to 4, the matrix was something like that. The same thing. So I don't know, let's try to, and that is the graph of the network. I don't know, we can try to make the example of n equal to 3, or we can actually also prove it in general why this is a solution for the multi-flop. Before we will understand why this is right, and then we can actually find a proof that uses the energy function to conclude that those are the right weights to get. So imagine I start from the state x that is all equal to 0. Okay. Imagine I'm in this state. What happens if I update one coordinate? I choose one coordinate I, and I update it. So I apply the Heaviside step function theta I, where theta I is equal to, I just told you, minus 1 of what? I'm doing all the weights times 0. So I'm doing minus 2 times 0 plus minus 2 times 0 So it's just the Heaviside step function of -1 applied to 0, that is 1. So basically, whatever, when I misstate all zeros, whatever I decide to update, I update xi. That xi becomes 1. Okay. So I don't know if I try to make a graph like to illustrate the dynamics. If I'm here, if I update x1, I will go to the state 1, 0, 0. If I update x2, I will put a 1 in x2. If I update xn, you get the idea. So this is this kind of Garden of Eden configuration, because I just ran away from that. So what happens if I have just a single one? It is a stable state, because imagine let's write it there. So imagine I update, like, I'm in a state like this. In which just xi is equal to 1 and xj is equal to 0 for all j different than I. Imagine my state is that. If I update a xj, what I obtain is that I do h -1 of what? All zeros, -2 times 0 many times, but then I have -2 times 1 for one coordinate, because I have xi that is equal to 1. So in the end, I have to do a h -1 of -2. No, this is wrong. So yes. So basically, if I update something else that was 0, it stays 0. So I stay in the same state. And if I update xi, xj was equal to 0, I was telling you, so it stays 0. Whereas when I update xi, I get all the others that are all zeros, because you do the weights of the things that are different from the one you're updating, because the weight on the diagonal is 0. So something multiplying xi is some 0, no matter what. So the result here is h -1 of 0, that is 1. So whenever I update I do in a vector like that, I stay there. So those are all stable states, basically. What I'm saying is that here, whatever I do, I stay here. Whatever I do, I stay here. Whatever I do, I stay here. Okay. What happens if I update, if I'm in a case in which there are more ones than just this one? Imagine there are 2 ones. Sorry. K equal to 1, with I different than k, and xj equal to 0, for O, J different than I, J different than Q. What happens is that if I update xj, you can try to make the same computation and you get 0. So if I update a 0, I will stay in 0. Update 0, so it stays the same. And whenever I pick one of those, either I pick xi, either I pick xk, if I have two ones and I update one of those, it becomes a 0. So I come back to having a single one. And this happens if I have even many ones. So what happens is that if you go down in this tree, and the bottom of the tree is all ones, whenever you pick a unit to update, you eliminate the 1 and the 1 becomes 0, whereas the zeros stay 0. So you will converge to this thing. So the upper part of the tree goes down, but also the lower part goes up. And those are the only stable states. This is just like a way of, but you can try to make the computation yourself for this case. I think it's very interesting to learn. But yeah, the idea is that this is the set of stable states, and stuff converges from the top and from the bottom. How can we prove that actually this is a good solution? Because I gave you already the solution. Like last time I was telling you about how we update the weights in order to have a network that does something. For example, to use the perceptron learning algorithm to find the weights of a certain upfill network, because there was this equivalence, okay? In this case, I gave you already the solutions, but how do we come to this solution that works? There's a cool proof, I think, in my opinion, that I wanted to do. I don't know if you want me to write the dynamics for all this stuff. Probably for the case equal to 3 would be nice. Just to have it somewhere. For the case I have to do. Yeah, it's a bit chaotic, but I don't know. I think it's very. Yeah, one. So let's try to prove, to give a better explanation. So, do you agree that if I have a single one and all the others are 0, then the sum do you see if it's green?
Just write a bit bigger than that because people online can see it that well.
So this thing should be equal to 1 if there are all zeros and just one single one. So if I write this should be equal to 0 when this is equal to, like for the states that I want to be stable states. And I do this to make it positive. So now I say this is the energy. And I'm just gonna try to write it in a form that is equal to the equation of the energy, in which there are the weights and the thresholds, and I will find the weights and the thresholds. Because this energy is minimized when this is equal to 1. This is always positive. This is just always positive or equal to 0, right? Non negative. But this is minimized when this is equal to 1. So actually, the stable states are the only local minima for this function. So this should be the energy, because I told you last time that the stable states are the local minimum, for points of minimum for the energy function. So if I find a way to write this energy, like the equation that I just showed you at the beginning of the class, then I will find my weights. And like this solution will kind of appear. That's the idea. I mean, it's not a crazy idea for a proof, but like it doesn't use any algorithm. It just comes from the fact that the sum of all the entries of my state are equal to 1 at the stable states. So yes, now we have to do some computations. Do you agree that this is that product? The square of the first minus the double product plus 1. Now, if you do this, I hope you've seen this sometime in your life. It's not a shock that this works this way. Okay. Yeah, so I can put the squares all together. Now, these are 2, but I have to remove the 2 if I said this. If I said that I has to be different than j, ij and j are separate in this sum. The 2 is not. You don't have to put the 2 here. That's why. No, minus 2. Now what? Remember that our xi's belong to 0 and 1. What does it mean? It implies that xi squared is equal to xi. Because 0 squared is 0 and 1 squared is 1. So I use this information to say that this is just, I can take away this square for this reason. So this I do the difference with this. So what do I do obtain is that minus I mean, +1 doesn't matter when you calculate the minimum. The minimum of a function and the minimum of a function +1 doesn't change anything. So I wouldn't really care about this +1. But let's try to write this. Let me recall the energy function of output. Maybe not. I mean, there was a hard term here, so I divide and multiply by 2. Right? This Let me call you the definition of the energy. I different from B just because the diagonals are zeros. And I'm using also the fact that it's symmetric because I can switch in this. Then so this is the first term with a minus. This is minus. Because I do -2 + 1. So -1. So this is minus something. So I can say plus sum over I of -1 It's right, it was already good. This term becomes this term. So there was already a minus xi +1. So I don't care about the +1 because the +1 is not important for minimization. And this is my W's, and these are my thresholds. That's why all the W's are equal to -2, and all the thresholds are equal to -1. And that's it. So it was a way of using the energy for proving, for finding the right ways. Not usually like possible to do it in this way. In this way, like our states had a particular property. So the fact that the sum of all the coordinates was 1, and they were the only minimum for this function. For example, 0, all zeros is not a minimum for this function. Because the value of this in all 0 is 1. Whereas it's 0 in the vectors that have only one coordinate and all zeros in the others. So this is the last upfield thing that I'm doing. Are there any questions? Am I jumping between topics too fast? That's what you wrote. Someone wrote on the anonymous chat, by the way. So do you have any questions? So let's move on to probability then. Yeah, you can see.
Infinity. Infinity.
Oh, it's fine. Okay. So from now on, like the reference book is this one that is about independent component analysis, in particular chapter 8. We put you a link on the Moodle. But like today, I'm not going to talk at all about independent component analysis. To do that, you need some maths preliminaries. If you did like maths before, like if you're like your bachelor or master is in mathematics, probably you don't really care about this part of the class. But I think it's important to do it anyway, so just to fix the notation. And also, yes, there are some topics that are a bit weird, like this kurtosis concept is not a big deal, but it's not usually treated in every course. So I think it's good to have a common basis since like all of you come from different backgrounds. So, and all these tools will be useful for next time's class. So first of all, even like there are actually two types of preliminaries that we need. One is change of basis in linear algebra, and another one is like some tools in probability theory. So I'm going to talk about changes of basis. It's not a crazy thing, but independent component analysis is essentially a change of basis. So we need to know what a basis is and how to change it somehow. I'm just going to make an example. I think there is many reference around. If you write on the internet canonical basis or change of basis, you will find like everything. So I don't think it's necessary, but again, like it's not jumping from different topics. It's just that these concepts are needed for next time's class. So whenever I write a vector, let me call this vector x, and I will write it as a column because I'm bored. Up to now, they were rows. I'm sorry. Imagine that this is my vector. Whenever I write coordinates of a vector, I'm implicitly assuming that those coordinates are written with respect to a basis. So I will add a notation like this. This means that this vector is written with respect to the so-called canonical basis. The canonical basis is a couple of vectors, a couple of axes. With respect to, I write the coordinates. It makes no sense to talk about coordinates without a basis. If you don't mention it explicitly, you're kind of implicitly assuming that your basis is the canonical one. The canonical one is this, 1, 0, 0, 1. So meaning that those two numbers are the coefficients that I put when writing this vector as a linear combination of the vector of the basis. So it's like -1, the first vector of the canonical basis, 1, 0, +2, the other one. And the whole point of talking about changing a basis means that what if I change those vectors? So what if I choose a different basis B, different vectors? I can ask myself the questions, what are the coordinates of the same vector x in this new basis? Let's not call it, let's call it B. So imagine that I introduce you a different basis and I write it with coordinates in the canonical basis. So we'll have the C here for the same principle. Like whenever I write a number, the number is written with respect to a basis. So when I ask myself, what are the, so you want, these are the coordinates of the vector V in basis C. When I ask myself, what are the coordinates of the same vector, but in basis B? I'm asking myself, what are these two numbers, alpha and beta? And those numbers are such that they satisfy this condition. So that my vector, when I write my vector in basis C, this is equal to alpha, the first vector of the basis B, So when I ask myself which are those coordinates, I have to do some computation like that. So in this case, someone can tell me what are alpha and beta. Yes, so in this case, let's why? Because B is the second vector of this basis B. So we call 1, 0 the first vector and 0, 1 the second vector. Let me put the line here. So one can ask also himself or herself what is the how do I find in general what is a matrix that does the change of basis? So I don't want to do it just for a single vector, but I want to do it for any vector. Whatever vector I take, I want to find a matrix that, given a vector written with respect to the basis B, gives me back a vector written with respect to the basis B, or vice versa. What did I write here? Yes. So imagine I have a vector with coordinates v1 and v2, written with respect to the basis.
A bit bigger, Nicholas.
Maybe that. There are another. So I have a vector v1 and v2 written with respect to the basis c. What can I do is to do the same thing. So I want a matrix such that matrix P, such that given a vector with respect to the basis B, gives me back the vector written with respect to the basis C. So the change of basis from B to C. I'm looking for it. It's not crazy idea. I'll try to find those coefficients alpha and beta, as I told you before. This is the first vector of the basis B plus B minus 1, 2. But this is like having a matrix like this multiplying. I call this matrix my matrix B. This is alpha and beta that are the coordinates of the same vector with respect to the basis B. So this way I found a matrix that does the job for any vector. Notice that as columns of this matrix, I have the vectors of the basis B written in the matrix in the basis C. So the opposite of what the matrix P does. Because P takes vectors from the basis B and goes from the basis to the basis C. But if I look at the columns, those are actually the vectors of the basis B written with respect to the basis C. Why is that? Like, I don't know if you ever tried to think about it a little bit deeper to these things. So imagine that I'm doing a change of, sorry.
My matrix P, I think the last class.
Yes, thanks. So imagine I have a point here, X. So my vectors are points, I'm in R instead of Rn. And I want to do a change of basis. And I want X, that is, imagine that X as coordinate 1. Because I have just one coordinate on R. If I want to change the basis, so I change the origin. So I want X to be 2. So I want the new coordinate of X with respect to a new reference frame to be 2. So the coordinate of X goes in this direction. But the coordinate of the 0 has actually gone here. The new 0 is here. Like I'm moving this 0. Like what I'm trying to say is that the coordinates of the point move in one direction and the basis moves in the opposite one somehow. If the new coordinate of x is 2, x is now 2. It means that I moved the origin back. So the coordinates of all the points are becoming +1, but the 0 has regressed somehow. Because the old 0 is now 1. And the same holds, like, I don't know, if you try to do with rotation, like if you have a reference frame and you want to rotate it, actually the axes are rotating in the opposite ways if the coordinates should rotate in a certain direction. Sometimes in physics, they refer this to as passive, like active, like action of the reference frame. Yeah. But this was it. Like it's just like a short recap about like the difference between changes of basis, just because ICA is a change of basis, just in a different context. I think we do a break now until 5 minutes, and I'll see you later for some like notions of probability, but nothing crazy, like average. Okay. Yeah. So this is a different topic from the one that I mentioned before, but we needed this for independent component analysis. I mean, there is many ways of introducing probability. If you did maths, you start doing that with the notion of sigma algebra and stuff like that. But so today I'm not gonna use that. Like, of course, it is on the background, but kind of we can like have an introduction to probability, just the things we need for the next topic. So I'm gonna like introduce. Yes. Some of the topics that are random variables. So can I do that without sigma algebras? Kind of yes, but it's hidden. So if you come from mathematics, you would agree with this, but there's like a bigger framework to talk about random variables in a single shot. But so we can define what are discrete and continuous random variables. Let's start from the discrete case. And by discrete here, I will mean discrete with a finite amount of values. So a discrete random variable is usually called big X with values from n values, so like tiny x1, tiny xn, that are real. So we're always considering real random variables here. So how do we characterize it? How we define it? We give to any of these tiny x's a weight, so a probability of being catched. So for example, imagine that this is my real axis, and this is my x1, x2, xn, okay. For each of those, I put a weight, for example, P1, P2, imagine that, let's put the weights here for some reason. So I have P1, P2, yeah. So to each of these values, I'm assigning a weight. That is the probability that that value will be catched. So I say that the probability that x is equal to that tiny x is pi. So since the probability of getting something is 1, the probability of the sum, so the sum of all the weights should be 1. And this is all I require. So whenever I give you a set of values that my variable can catch and a set of weights, that's it. And those weights tell me what is the probability of getting the ith value. So before that, yes. So you probably have seen, or at least once in your life, these things, that the average and the variance. The average sometimes is called mu, sometimes expected value. you have like whatever terminology. I use this notation for the average. I don't know if you have a different one, is fine as well, but it's just to fix the notations that you will find in the exercise. So basically all this is useful for doing the exercises of this week. That's why. And the variance, I don't know, probably you've seen like different ways of writing that. Maybe I don't have to rewrite it again, but like the variance of a random variable x, in general, not just for those discrete ones, is the average quadratic distance from the average. So I do the distance from the average, then I do the square, and then I do the average outside. But since the average has some cool properties, I can like do the product inside, and then I get the formula that is on the second line. So the variance can be written as the average of x squared minus the average square of x. And all these can be written using the tiny pi's. So either using the first formulation, either the second one, and I do the variance. You see that like the average is like the weighted sum, kind of what we saw before. Like you have the weights and you have the values that your variable can get. So that's it. Probably you didn't see this. I don't know, depends. There is these things that are called the kth moment. So you can see the variance as the moment of order 2 minus the square of the average. But when you write the variance in this way, this is an easy proof to pass from this to this. I'm not going to do it, but minus this. This is actually the second moment. And by moment, I mean this. So the average of x at the power of k. So I do the pi's, multiply the x at the power of k instead of just x as in the average. If you want, the average is the 1 moment. The variance uses the 2 moment, and then so on. So those moments are actually like showing some properties of your probability distribution, also in the continuous case, we will see later. But essentially, so the variance tells you like how sparse is your distribution, whereas the third moment is called also skewness and tells you how symmetric it is with respect to the average. So something that is very symmetric and centered in its average has skewness 0, whereas the third when the skewness or the third moment is negative, you're like asymmetric towards the left or asymmetric towards the right if it's positive. And actually, we are going to use in the exercise the fourth moment that is called kurtosis. So I'm going to tell you later what it is. But essentially, the idea is to be that it's called the tailedness. So like, how are the tails of your distribution? So are there many outliers or very few outliers? This is the idea. So before this, I wanted to make some like very, very easy examples of like discrete random variables. Just to fix the notation also, it's not like, I don't know, probably you've seen this Bernoulli. Bernoulli was a family of mathematicians, so whenever you find Bernoulli, you don't know which brother it is. But yes. So, and I say that x goes as Bern of parameter p. It's a distribution such that the probability of x is equal to that takes values just 1 and 0. The probability of getting 1 is p. And the probability of getting 0, since the weights have to sum to 1, is 1 minus 2. Because the sum of this should be always 1. This is like p1 and p2. Okay? So you can calculate the average, and the average is p. Why minus p? Because I have to do x times, so those are the x's, x1, x2. I have to do p times 1 plus 1 minus p times 0. So it is equal to p. And you can calculate the variance as well using the formulas that I gave you before. Should I do that? Yes. But this is the distribution of flipping a coin. So P is the probability of, like, if you have a good coin, like a normal coin, you have P equal to a half. Otherwise, you have like P, so it's a tricked coin that has like more probability to get in head or tail. Variance of X is equal to, I do the second moment, minus the average square. The second moment is equal to what? I do P times 1 square plus 1 minus P times 0 square, and then I do minus P square. So, yes. So it's P times minus P. So there is another example that is very famous, that is the binomial distribution. It is basically the idea that instead of having just one coin to flip, I have many coins to flip. I have a stack of n coins, so gives me the probability of getting, if I win when I get head, of getting k wins over n trials. Exactly k wins over n trials. So I can say that X is called the binomial, we call it bin of n trials and parameter P. The values it gets are from 0 to, let's say, n. So I can get 0 wins or n wins over my n trials. And the probability for k, so for k that belongs to this set, the probability that X is equal to k is given using Newton's binomial thing. That's okay. Have you seen this in your life before? How many haven't seen this? You didn't see this before? Okay.
I mean, this is specific, but
This, like this notation? No? Okay. So this is called Newton's. If you Google this, you find many more information than what I can say here, but essentially it counts the subsets of cardinality k in a set of cardinality n. So if I have a set of n elements, this thing tells me how many elements, how many subsets of k elements I can find inside. This is also equal to, oh, am I doing this right? Okay. Where by exclamation point, I mean that if I have a number a and I do exclamation point, what does it mean? That I do a times a minus 1 times a minus 2, etc. times 1. So all this to say that the probability of getting k wins is this, p at the power of k, 1 minus p at the power of n minus k. So to verify, for example, that the sum, I told you that the sum of the weights should be 1. You have to verify this, that the sum of n over k, p at the power of k, so the sum of that k goes from 0 to n, 1 minus p, the power of n minus k. This thing is called, so there is this formula. It's like this plus this at the power of n. This is the development of p plus whatever it's inside here, 1 minus p at the power of n. This is also a very classic thing. How you develop this? A plus b at the power of n is equal to this formula here. And so here you obtain, this is p minus p, I obtain 1. So the weights sum to 1, everything is fine. It's an actual like discrete probability distribution. before talking about the average and the variance of this thing, I think it's easier to show some properties of the average and the variance. Why didn't I do that? Yes, these things that hold for everything, actually, not just for these discrete, but also for the continuous ones. Not gonna prove those, but they're not very hard to be proven either. So if I have if I have two random variables, x1 and x2, and I do a real number times the first one plus a real number times the second one, I can take the real numbers outside and do the sum of the average of those. Say the linearity of the average. If I have x1 plus c, if I have a constant, I can put the constant out. And what happens for the variance? The variance, if I have a constant, a real constant, it comes out, but with a square. And if I have plus a constant, the constant disappeared because the average is like the variance is a distance. So I don't care. It's a relative distance between the average and my variable. So if I add a constant, they will cancel out because there is plus the constant and at some point there will be minus the constant. So that's why this last property is true. Is that true that I can, the question might be, can I do this? If I have the variance of two random variables, x1 and x2, can I do this? Is the question. No. Not in general, at least. Why? If you try to write the variance of x1 and x2, you have two extra terms. More than these two. So if you try to write what is equal to this, you have plus something else. And this something else is, if you want, I can write it down, or do you want me to do the proof of this? How many no's? Should I do it? Okay. Jump to another topic. I mean, it's not a very crazy proof, I think, but so I have to write variance of x1 plus x2 is equal to the average of x1 plus x2 squared plus the average squared of the one. You have to do all the computations, not very nice, but you use the linearity, so. For now, by linearity, I can split those, so let me cheat. If you do that, you recognize the variance of x1 here. So it's equal to variance of x1. And if you look at this, and this is the variance of x2. But then you have this 2 times what the average minus 1 is 2 minus the average. So the variance of the sum is not the sum of the variances, but almost will be if this will be equal to 0. This is called the covariance between x1 and x2. And it happens if that, I'm gonna give you just in 1 second the definition of independence, but it happens is that if x1 and x2 are independent, then the covariance, so this term, the covariance of x1 and x2 is equal to 0. The inverse is false. Don't do that. This is called the covariance. So let me talk about what it is. Mean.
One thing, do people know why we put these two in front of the equation? Yes or no?
Sorry, why are you asking this question? It's the two that is here and there. It's a two that was here and there. I just put it together.
No, I thought it was expected one of two.
No. It's just like a constant that you find here and here. You just put it out because what you do.
Remember?
I think this is by linearity of the average, and this was already out. So I just put it out. And are there any questions? So, yes.
What exactly did you mean when you say that the opposite is false?
If I have the covariance between the two random variables that is equal to 0, doesn't mean they are independent. They can be not independent. It's not equivalent. It's not having covariance 0 is not a characterization of being independent. Yeah. Let me say what independence means because I did not follow the order of my slides. So if I have n variables, I can do it between two. But if I have n variables that are discrete random variables as I defined them before, so the probability that the first, so, okay, there is that equation. That is the definition of independence if they have discrete finite values. So if I take n real numbers, the probability that the first one is equal to x1, there is comma because the comma means end in this notation. So the first one is equal to tiny x1, the second one is equal to tiny x2, etc. And the third one is equal to tiny xn. I put x, no, I put, okay. So the comma means and means also intersection between events. The probability that all that happens together is equal to the product of the single probability. Maybe I'm gonna define them also for continuous ones, but this is the definition of being independent. So why are we doing all this? Because if I want to calculate the average of a binomial distribution, I can see the binomial distribution since it is like n points that I'm flipping, n independent points. So it is, I can say that x binomial is equal to the sum, right, that goes from 1 to n of xi, where xi is Bernoulli of parameter p. So I have n in this, yes. Yes. Means variable with distribution, that a variable that behaves like a binomial of this parameter. Like you cannot say, yes, like that the distribution of this random variable follows this law. Yes, might be a weird notation. Like it depends on the where you have studied that. It's not common. Let's see. That's why I did also this part of the class to fix the notation. I like to. Yes, that's a good question. So it means behaves like the one. Okay. So the binomial distribution is the sum of n independent coins. So when I want to calculate for example, the variance and the average of this, the average I don't need independence to have the sum. So I can say that the average of x, so is the average of the sum that I goes from 1 to n of these xi that are Bernoulli. But then all these behave the same, so this is like but this is equal to P for all I. So I have n times P as the average. For this, I don't need independence because I'm just using the linearity of the average and the fact that they all have the same distribution. So I say that these xi's are said to be IID. What is this? Independent, identically distributed. They all have the same distribution for all I, and they are independent. To prove that the average of the binomial is NP, I don't need independence, but to prove that the variance of this thing is linear, I do need the fact that they are independent, so I have the variance of x, that again is the variance of the sum independent. And this is equal to P times 1 minus P for all I. So again, this is equal to N times P 1 minus. One could have also calculated the average and the variance using the definition of average and variance, but for this distribution. But this is cooler because I did this easier thing. Yeah, it's a bit chaotic. Let me cancel something like this. Are there any questions so far? Yeah, I suppose we're gonna talk about random variables with density. So not all the random variables have a density function, but I want to talk about only the ones that do have a density function. What is a density function? It's the continuous case of giving weights to singleton, to single points, like I had before I had the finite values, for example, 0 and 1, or for this random variable, I have this set that goes from 0 to 1, and for each of those, I give a weight. Now, imagine that I am on the real numbers, so I have an interval A and B. I want to find a continuous way to give a weight to all the points in this interval. And that is a function that is called a probability density function. So it should be to satisfy the same condition as before. So the sum becomes an integral. And like the integral of the function should be 1, because before the weights were summed to 1. And here, if I pick a single point, it's always 0, because the integral, like, I will not get anything. The way I calculate the probability this time is that I calculate the probability that the random variable belongs to the interval AB. Using the integral. So I integrate from A and B the density function of the random variable x. This gives me this area basically. And if A is equal to B, I will get always 0 because it's an integral between two extrema that are the same. That's why the points here are 0 measure, we say. Yeah. And the function fx needs to be measurable. I put that hypothesis and non-negative, but needs to be measurable because if it's not, I cannot write an integral. Integrals need to exist. That's why I need that hypothesis. Just like, otherwise it doesn't exist. So this is the way in the continuous case in which I calculate probabilities. So the average, I do the analogous thing. So I multiply by x instead of by the single axis in the sum. I put x density. and that's how I calculate the average. Again, that integral needs to exist. So all these definitions are under the assumption that all the integrals can be calculated, so they don't diverge, they don't go to plus infinity, for example. So the variance, you do the same thing as before, but you put x squared minus the average square. You can use also the other definition. It's the same thing. And the kth moment, again, you put x at the power of k, density. Analogous case, but with an integral instead of a sum. And we are assuming that this density function fx always exists and always behaves nicely. Whenever I put it in an integral with something else, the integral is finite. So I can compute it. Yes. So this is the properties that hold also for those continuous variables with density. I can make an example of a continuous variable, random variable that is very famous, I suppose. That is the normal distribution. I mean, probably this one you've seen it, all of you. So again, I say that x behaves like a normal distribution of average move and variance of sigma square. It's called sigma square because it's always positive, and I call sigma. Again, to say that something is a normal, a Gaussian, I can just define what is its density function. That is 1 over sigma square root of 2 pi e at the power of minus a half x minus mu divided by sigma square. So this is its density function. The variable is here and depends on the parameters mu and sigma. And when one calculates the average, you just put this in the integral with x and you get the average. The integral is very horrible, but the result is mu. And again, for the variance, I'm not asking you to calculate that like ever, but like the variance is with the formula with this density function. And you have seen probably like Gaussian distribution all over the place in your studies. So, but is it like this function falls in that category somehow? So I told to you about moments. The moments are these integrals, and tells you property about the distribution. So in particular, I was telling you that the third moment tells you about the skewness. So whether a distribution is like this is the average of the distribution, let's say, if it's very centered or if it's like very misplaced. So this is like skewness 0, skewness negative, and skewness positive. This is a characterization of the moment of order 3. But we're going to use the moment of order 4. That is the excess the kurtosis, sorry. But before that, I need to introduce this function that is called the moment generating function. Is a function such that if I calculate its derivatives and I put 0 instead of t, that is so it's a function of the variable t. If I calculate the derivatives and I put 0 instead of t, if I do one derivative, I will obtain the first moment. If I do two derivatives, I will obtain the second moment. So if I do k derivatives, and evaluate that in 0, I will obtain the kth moment. So it is like an easy way, like skipping the integrals and kind of like hiding them, but to obtain the moments. So why it is possible also? This is a kind of I'm hiding something, but yeah. So the moment generating function is this function of a random variable x. Just writing that, you need some assumptions because you are like writing an integral of something weird. So it means that you have to assume that the integral exists so that the function is integrable. But even more, for example, when you calculate, so this k here means k times the derivatives. So you calculate the derivatives k times. Or you can write also, yes. You can write also dk dtk xt. And you say, okay, I can do the derivative because, like, for example, if I do it once, I'm derivating with respect to t. These x will fall out because the derivative of t, like this is a constant when I derivate with respect to t. So these x will fall out. And I will have many x's falling out the more I derivate. So it's clear that I want this to be equal to x at the power of k e x. But pay attention that here we're kind of like putting the derivative inside the sign of integral. So there is a theorem to do that. You're not always allowed to do that. And probably the reason why is that you need the integral for each derivative to be well defined. You don't want integrals to explode to infinite. That's the reason why for every of these steps, actually, there are hidden hypotheses, let's say. But let's imagine where like everything works just fine. You're like, you have your, I don't know if it's clear, but like you have the power of k, you have an integral over r of e t x f x x. Yes. And I want this to be big here, so I can end it with respect to t. My integral is with respect to x, so everything is fine. But to do that, there is a theorem. So everything should satisfy nice assumptions. In particular, the integrals should be well defined. But yes, all to say that, imagine I can do all this. Imagine I can integrate and everything is fine. I get here. When I do the case derivative evaluated in 0, this becomes 1. If I evaluate in 0, there is also this notation, t equal to 0. So I derivate and then I evaluate in 0, t equal to 0. So basically I put 0 here, this is 1. So I have the case moment. So if I give you explicitly this function, you have a nice way of calculating moments of all orders, since we need the fourth order moments for independent component analysis. So what is kurtosis and excess kurtosis? Oh, yeah, before that. What happens if I have a random variable x, and instead of doing x, I'm doing x minus its average, mu? So here I have the average of x, but the average of this new variable is 0, right? By linearity of the average, I obtain the average of x minus mu, but this is mu. So this is 0. Okay. Again, imagine that I did that, and now I want to do something else. So I want the variance to be 1. So now I take x minus mu and then divide it by sigma. What is the variance of this thing? I do the variance of x minus mu divided by sigma. Using the properties of the variance that I told you before, you obtain the constants in the variance. I told you that when they pop out, they pop with a power of 2. So I obtain 1 over sigma squared, the variance of x minus mu. But I told you also that doing the translation doesn't matter for the variance. So I have 1 divided by sigma squared variance of x. But this is x sigma squared. So this is 1. So these operations are a way that if I have x and I go to this, I put my average to 0 and my variance to 1. It's not. is something very common. But so, the kurtosis is the fourth moment of a random, is defined as the fourth moment of a random variable, but the random variable, you do these operations before calculating the fourth moment. So instead of calculating the fourth moment of x, you do it for this manipulated x. And that's just the fourth moment. And then there's people who said, oh, let's call this excess kurtosis. What does it mean? I just put -3, random number. Why this? The reason is that if you take a Gaussian distribution, even like no matter what are mu and sigma square, since it's defined in this way, the excess kurtosis is always, sorry, the kurtosis is always equal to 3. For some reason, the Gaussian has excess kurtosis equal to 3. One of the exercises of this week is, I think, proving that. But you will use the moment generating function, so it's doable. And so the excess kurtosis, since it's 3 minus 3 is 0. So what does this kurtosis mean? Both of them are like representing some properties of the tails of the distribution, so the outliers somehow. You take as reference the normal distribution, since all the normal distributions have kurtosis equal to 3. And you see that there are, probably this is like, so okay, there is this terminology called mesokurtic if it's like the normal, the same as the normal. Platkurtic if it's like bigger, and leptokurtic if it's smaller, something like that. Yes, or the contrary. Let me check. Leptokurtic is if it's bigger, and platykurtic if it's less than the normal. So the idea is that if you take one that has, for example, excess kurtosis equal to 3, so the one that is red, you see that the tails are bigger than the tails of the Gaussian, that is the blue. Whereas, for example, the red one has smaller tails. So it tells you how many outliers are there or not. And this is the idea. And actually, having excess kurtosis equal to 3, I think it characterizes all the set of Gaussian functions. So I think only the Gaussian functions have excess kurtosis equal to 0 and kurtosis equal to 3. Yes. So this seems unrelated, but again, we will use it in the next class. There is this concept called weak convergence or convergence in distribution, convergence in law. It's a definition of convergence given a sequence of random variables, xn. With that notation, I mean a sequence, x1, x2, xn, but n that can go to infinity. So it's a random variable that depends on the variable n. So I have a sequence of real random variables. I say that they converge in law, or again, converge in distribution, or converge weakly. And I use the notation D, but there is many notations out there just to fix one. If the probability that, given an interval AB, the probability that xn falls in the interval AB tends to the probability of the limit falling in AB. It's not like a classic limit, it's a limit using the probability that. So the behavior, if you want, of the elements of the sequence xn behaves like the limit for n that tends to infinity. Okay, I need to define this theorem that is used next time. So if you have, again, n random variables in L2, what does it mean L2? That the average of xi square is finite. So I have, this implies that the moment of order 2 is finite too. It means that the variance is finite as well. So like everything is okay. It's just an hypothesis. We don't need to prove this theorem. But so I have these random variables, and the hypothesis is that they are IID. Again, what does it mean? They're independent, identically distributed. Identically distributed means they have all the same average, all the same variance, they have all the same distributions. So it means that for all I, xi behaves like the same thing with the same parameters, okay? Like before in the Bernoullian that had all the same behavior that summed to the binomial. So I say that if I sum all of them, the variance, okay, the square root of the variance is that, like I just put a parameter. So I define what is the sum of all of them. I define the sum n as and let's think a little bit about this. So what is the average of Sn? The average is linear. So as we did for the binomial before, this is n mu. Because the average splits the sum. Each of the terms is equal to mu, so I have n times mu. Okay? What happens to the variance of Sn? They are independent, so the average is linear. Sorry, the variance is linear. The average is always linear. The variance is linear only if they are independent. So if they are independent, the variance is linear. So I can do that by independence. So I can do n times sigma squared. So in particular, I can say that if I want the sigma of this variance, it's supposed to be like, I don't know, a big sigma squared, something. Sigma, it's a mathematician, yeah. The square root of n times. Why am I doing this? You see that now I'm considering the sum Sn minus the average of Sn. So I'm doing this Sn minus n mu, so it's average, divided by square root of n sigma. So I'm centering it or normalizing it. The same operation as I told you before. You say minus mu divided by sigma. Okay. And so it's that.
Yeah, I did that earlier for some reason. My
Well,
computer
good.
did that as well.
But yeah, okay, let's try to do it without. What happens is that this kind of cool. Like I can treat sums of things that are kind of equal at the limit as a Gaussian. And that's it. Like this is the result of the central limit. And so we can rewrite one things in a different way. So we can write that the probability, this is equivalent. The fact that for every A and B real number, the probability that Sn minus n mu divided by square root of n sigma belongs to the interval in B. Hence, for n that goes to plus infinity, this is like a normal limit. This is not. This is what I defined before. That's the values of D. But this means this. And the probability that a Gaussian distribution of centered in 0 with variance 1 belongs to the interval AB. So if I pass things to the limit, things behave like a Gaussian, a sum of like things that are just independent. They can be anything. I didn't put like many heavy hypotheses. It's kind of a cool theorem. How do I? There's another way of writing this because I just told you how we calculate the probability that something continuous belongs to an interval. This is the integral of AB. Maybe I can write this is the weak convergence, yes. I have to put the density function with. But the density function was 1 divided by sigma square root of 2 pi e at the power of all these things. This isn't no, it's wrong. Minus x minus 4. But this is a normal distribution of 0 and 1, so this is 1 squared divided by 2 squared. But sigma is equal to 1, and the average is equal to 2, so this is just x squared divided by 2. These integrals are very painful, but that's how you have a way of calculating this. I think this is it. I don't know. We're gonna use this next time, so we have it ready. And yeah, I think, are there any questions? This is also my last class, so if you have any questions, I won't be here next time, so feel free to email me if you have questions about my part of the course. And are there any questions now? So, I think that's all. Yes. Yes, yes. Abilidad means minus infinity plus infinity. Yes, sorry. Yeah, means, is that like, all right? Yeah, I think that's it. We will put a poll for the second trial for the exam in January, so you can choose which date you prefer. And the first one is the 16th.